Now, to talk about electrons, we're going to focus on valence shells, electrons. The valence shell is the outermost shell, and those are the ones represented in that large colorful table that we showed at the beginning of this discussion. And there are some fabulous patterns, once you understand them, that make all of this so much simpler when we see what's happening in the periodic table. And it's just elegant, if you will, that the scientists in the 1800s came up with a pattern that we still use today, and it really all bases on electrons that they didn't really even have any understanding of at the time. So, outermost shell electrons, valence shells, are going to be our ticket to understanding how we put things together. Because the group number for main group elements is going to tell us how many valence electrons there are. So main group elements are those whose names, the group numbers, are given with A, so 1A, 2A, etc. Their group number corresponds to the number of valence or outer shell electrons. So group 1A includes things like lithium and sodium. The last electrons for the lithium electron configuration, the outermost, the valence electrons, are 2s1. For sodium, it's the next row down, so the outermost electrons are in the third shell, but it's again s1. And so ns1 tells you that n is the shell number or the principal quantum number, and one valence shell electron for group 1A, regardless of which shell the last electron, the valence electrons, are found in. For group 2A, we could do the same kind of thing. So group 2A would be things like beryllium, which ends with 2s2, or the one below beryllium is magnesium, which is going to end with 3s2. Anything in group 2A is always going to end with some outer shell and 2 electrons. So group 2A has 2 outer electrons. It becomes very orderly when we see that. If we go to the other examples here, this would be chlorine and bromine. If you recall where they are, they're in group 7A. And 7A, if we look over here, should have 7 valence electrons. Well, there you have it. Remember that the outer shell is represented by the 3 in the notation for chlorine. Chlorine is in the third row, which is where the third shell electrons first are observed. And so the valence electrons for chlorine are 7, all in the third shell. 2 of them are s orbital electrons in the s subshell, and 5 of them are p subshell, p orbital electrons, for a total of 7. Bromine is one row further down on the periodic table, and so its outer electrons are in the fourth shell. And the last electrons, the outermost electrons, the valence electrons for bromine, are again going to be 7. So the outer shell for bromine turns out to be the fourth shell. So 4s2, 4p5 gives us the 7 valence electrons for bromine. Let's pick another one to do just to see how it works. So let's pick, something in between. How about group 5, 5a? And that would be, the simplest one in there would be boron. The electron configuration for boron is going to have the outermost, the valence electrons for boron. I just put beryllium instead of boron, fix that. Boron will have the same as beryllium, but 1 more electron. So it's going to have 2s2, but then after that becomes 2p1. Well, here you have 3 valence electrons because 2s and 2p are all the same shell, and that is a total of 3 valence electrons, just as shown. I did group 3. That was group 3, not group 5. Well, silly me. Group 3A will have this pattern with ns2 and np1. The third electron is in the p subshell. Okay, now I will do group 5. Well, if I read the right column, it would help. And not element 5, but group 5. So group 5A, well, let's start with nitrogen. And its friend below there would be phosphorus. And so the outermost electrons for nitrogen will be 2 more than boron. So we'll have 2s2, 2p3. Well, there's your 5 outer electrons as 2 are electrons in the s subshell, and 3 are in the p subshell. If you went to phosphorus, phosphorus is in the third row, so its electrons, its outer electrons are in the third shell. Analogous to nitrogen, it would be 3s2 and 3p3 for its valence electrons. Again, they're going to have 5 valence electrons because that's the way they all work in group 5a, and the pattern is always the same with 2 s subshell electrons and 3 in a p subshell. All right, so we could do all the ones in between, but I think you kind of see the pattern. Here is where the periodic table is your ally in understanding the organization of the electron configurations. Thankfully, the arrangement of the periodic table is positively slick. It gives us a method for remembering the order of orbital filling, because if you go from the top left and move across successive rows, one atomic number greater at a time, you get the proper order, the correct order of filling of subshells. So follow this pattern and see where it goes. You go from 1s, and when that's full, then to get to the next larger element at atomic number, we have to go to 2s, and from there we go to 2p. When those orbitals are full, then next we'll come around to 3s. When those are filled, the next ones to come will be 3p. When the 3p subshell is filled, we go to 4s. Now, here is where the funny part came in that makes us a little bit confused. The d electrons follow after 4s because they're in lower energy level than the 4p. The 3d electrons will be filled, those orbitals will be filled before 4p orbitals are used. Now, notice that each of these follows in order, and after 3d is going to be 4p, and this gets us up to number 36, which is krypton. And you do not have to work your way past this, so don't panic yet. But you could take this all the way across, and the f orbital electrons only show up when you get down into the 6th row, and that's another whole matter altogether, but let's not go there for today. The point of it is each of these blocks of the periodic table are color-coded to represent where the last electrons fill in that portion of the periodic table. The s block has electrons. The outermost electrons are going to be in s orbitals. The p block is on the right, and for those elements, the last electrons in their configuration are always p electrons. So the s block and the p block together are the main group elements. Those are the ones that are the easiest for us to remember and for us to follow their the valence electrons, because they correspond to group numbers. The group number equals the number of valence electrons. The d block and the f block are transition elements, and those are the parts, the transition metals. They're all metals, yes. Those parts of the periodic table that are color-coded with the orangey color for the D, if that looks orangey to you, and the red color for F, is the last electrons are going to end up in D or F subshells. They're always a little sneaky to think about, but the first pattern to notice is that the third shell is the first place that any D electrons occur. And so when you're in the D block, the transition metals, that is going to begin with 3d electrons, and each row is going to have a higher shell and subshell level of d electrons. The f electrons, I agree, are not the easiest to recall, but they only occur when you have finally hit the s subshell. Oh dear. Well, good thing we don't have to know that. But the fourth shell is the first shell that has any f electrons, but they energetically do not occur until after 6s. But the blocks of the periodic table are your ally. So if you can remember the s block, the p block, the d block, and the f block, it makes it a lot easier to keep track of how the electrons fill in proper order for every element. All right, I'm going to let that be enough for this recording for today, and we'll finish that conversation at a later time. I hope that helps you make some sense of all those elegant patterns, honestly. If you look at these this pattern here, I'm going to refer you back to where we started. The colors are the same on that initial diagram. And so what we see here are all the outer electrons, namely the valence electrons for each of the segments of the periodic table. The S block has electrons. The last and outer electrons, therefore, are all s orbital electrons. The p block has all elements with the last electrons in p subshells, p orbitals of the p subshell. And the row number corresponds to the first number of the subshell. When we're looking at main group elements, the transition elements are going to be off by 1. So when you get to the D block, the first row is going to have 3d electrons, in spite of its being in the 4th row, because the first d electrons occur in the 4th row. And then the F block are more complex than average, you bet, but they begin after you have come to the, be careful how you see that, to the 6s subshell, and the first F subshell is only in the 4th shell. Wow. So the F block, P block, D block, and S block helps us to recognize the outer shell electron patterns. Good luck understanding these, and remember, you only have to work your way up to krypton, so it's not quite as scary as you first imagined.